Hi everyone, welcome to lecture 18 of your electric circuit class, and we are going to cover in this lecture what we call the storage element, and we are going to talk about capacitor. So the objectives of this lecture: first, you need to know how to define a capacitor and determine its voltage, current, which is VI relationship, and the second objective is to obtain the current waveform from a voltage waveform of a capacitor, and the last objective is to obtain the equivalent capacitance of a given circuit, let's say. So when we are talking about capacitors, we can define capacitor as a device that has the ability to store energy in its electric field. It is usually consisting of two conducting plates separated by insulator, or we call it dielectric. So the most popular dielectric material is what we call mica. So the amount of charge on a capacitor, that is Q, is equal to C times V. So that will give us the capacitance value is equal to Q over V. This over here is charge in Coulomb. This over here is voltage in volts, and this over here capacitance in farad, which is F. So when we look at this equation here, we can define what we mean by capacitance. So capacitance is the ratio of the charge on one plate to the voltage difference between the two plates. So regarding the capacitor voltage current relationship, the current through a capacitor can be expressed as I is equal to C times dV over dt, which means that if we need to get the voltage of a capacitor, we can just take the integration of that formula. So V is equal to 1 over C. The integral goes from an arbitrary initial time to a final time of I dt plus V of T naught. This over here, that is what we call the initial condition. The energy stored in a capacitor can be determined as 1/2 times C times V squared. We may also use energy is equal to Q squared divided by 2C. So either formula that will give us the right answer. It depends on the given quantities. So now if we look at I is equal to C dV over dt for DC voltage, which is not changing with time, which means it's constant. The current through the capacitor is 0, and that means capacitor acts as an open circuit to DC. Why is that true? Because you look at this here, the dV. Since V is constant, so d of a constant over dt is equal to 0, which means that the whole thing over here, that our I is equal to 0. So since the current flowing through capacitor, we are talking about the average current that passing through a capacitor is zero. That means there is no current is flowing, which means that the capacitor is an open circuit in a DC. So let us go over an example over here to see how we can get a current waveform from a given voltage waveform. So we would like to find the current flowing through the capacitor if the voltage waveform is as shown. The capacitance is 100 microfarad, and this is our this is T, this is 1, this is 2, 3, and 4, and this over here is our VC of T, and the value here is 2. So this over here is the voltage waveform. And from this voltage waveform, we would like to obtain the current waveform to see how it looks like. I don't want anybody to be confused here. So what we need to do, we need to find the equation for this line, for this line, for this line, and for that line. So these are like from 0 to 1, I have an equation for the voltage. From 1 to 2, I have an equation. From 2 to 3, I have an equation. And then from 3 to 4, I have another equation. So as you know that this is from here starting as 0. So this portion over here, to find the equation for this line, that will be rise over run. So we can say V is equal to 2t, and that is t greater than 0 and less than 1. So now to get the equation for this line here, this is the best way so nobody will be mistaken. So this point here, this coordinate, I can express it as x, which is 1, and y is 2. And this point over here, that is really 2 for the x and 0 for the y. And then any point in that straight line, we call it x and y. Okay, so now we can write the following: y minus can say y minus, let's say, y1 over x minus x1 is equal to y1 minus y2 over x1 minus x2. This is, if you remember the slope equation. So now, if I call this as, let's say, x1, and this here is y1, and this over here is x2 and y2, then we can substitute. So y minus 2 divided by x minus 1, that is equal to 2 minus 0 divided by 1 minus 2. So from that, y minus 2 over x minus 1 is equal to 2 divided by negative 1, which is negative 2. So now our equation in this case, that will be y minus 2 is equal to negative 2x plus 2, which means y is equal to negative 2x plus 4. However, our x-axis here, x is t, which means that and the y is our v. So, and y is v, right? So we can say that v is equal to negative 2t plus 4. So that means our v is equal to negative 2t plus 4, and that is for t greater than 1 and less than 2. And then, so we finish the equation for this line. Now we will come to this line. That line is based on what we demonstrate here, how to find that equation for t greater than 2 and less than 3. We will have 2t minus 4, and then the last v, that is for t greater than 3 and less than 4, that will be negative 2t plus 8. So now we can say our v of t is equal to, for the first one was 2t, so that is equal to 2t when t greater than 0 and less than 1, and then we will have for 1 between 1 and 2 negative 2t plus 4, and then when t greater than 2 and less than 3, we have that to be 2t plus 4, and then for t greater than 3 and less than 4 came out to be negative 2t plus 8. So as you know, the current or the voltage current relationship for a capacitor, that I is equal to C dV over dt. So our I is equal to, the value of C is 100 times 10 to negative 6, because that is the capacitance value. And then dV over dt. So we will take the dV over dt for this quantity. That is 2. So the derivative of 2t is 2. That is for t greater than 0 and less than 1. And then it will become, for the second one, negative 2t plus 4. That will be negative 2. And then 2t plus 4 will become 2. And then the last one is negative 2. So this is our current, which means that is equal to 200 times 10 to negative 6, negative 200 times 10 to negative 6, 200 times 10 to negative 6, and negative 200 times 10 to negative 6. This is for t greater than 0 and less than 1, greater than 1 and less than 2, greater than 2 and less than 3, and greater than 3 and less than 4. So the waveform will be like this. This is our t. (200 times 10 to negative 6). This is the capacitor current IC, and over here negative 200 times 10 to negative 6. This is 1, this is 2, this is 3, and this is 4. 1, 2, 3, and 4. So now, between 0 and 1, that was 200, which is this. And then, between 1 and 2 is negative 200. Positive 200 between 2 and 3. And negative 200 microampere from 3 to 4. So this over here is the current waveform. So please, I would like everybody to pay attention to the following. Capacitor, voltage, cannot change abruptly, which means right away. So this here, it takes time to increase and it takes time to decrease. So this is okay. Takes time to increase. We cannot have something like this, because from this point to this point it decreases in no time, and that is not allowed. That is not allowed. We are talking about the voltage, okay? The second topic over here is about capacitance connections. The first connection, that is series connection. And for series connections, our formula to find the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3, and it depends how many, let's say, capacitors connected in series. And for two capacitors, in series, we can find our equivalent as C1, C2 over C1 plus C2. So it's exactly the same as the parallel resistors connection. So for our parallel resistors, we said that 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over Rn. And for parallel connection, we will just add those. So C equivalent is equal to C1 plus C2 plus C3 plus Cn. Don't forget that it is the other way around with respect to capacitors when we are doing the equivalent capacitance compared to resistors. Let us go over an example here. We would like to find the equivalent capacitance. So if I have this as 8 microfarad, 8 microfarad, this is 4 microfarad, this is 8 microfarad, 4 microfarad, and 2 microfarad. And we would like to find our C equivalent at the terminal over here. So our solution, if you look at these two capacitances, they are in series. So 8 in series with 8. In this case, 8 times 8 over 8 plus 8. And that is equal to 4 microfarad. So now we will have this. This is 4 micro, and this over here is 4 micro. So we can say 4 parallel with 4. Then we will say 4 plus 4, that is 8 microfarad. So now we are done with the whole thing over here. So then we will have 8 micro and 8 micro. They are in series. So 8 in series with 8, and in this case 8 times 8 over 8 plus 8, that is equal to 4 microfarad. So if you look, we are done up to this point here. So that will give us 4 parallel with 4. That is 4 micro. This is 4 micro. Then 4 parallel with 4. This will give us 4 plus 4, which is equal to 8 microfarad. So now the last one is this 2. So we will have 8, and then we have over here 2 micro, and this is our C equivalent. So 2 in series with 8, that will give us 2 times 8 over 2 plus 8, which is in this case that is equal to 1.6 micro. And this is our equivalent capacitance. So for this lecture, as long as you know the definition of capacitor, and capacitance. You know the voltage current relationship, and you know how to find equivalent capacitance, you will be in a great shape. That is it for today's lecture, and this is our homework. So we have two problems, and thank you for watching.